countdown.
Congratulations! This live broadcast is specially brought to you by Academy YouTuber Malaysia, an initiative by Didik Malaysia and Kelab Guru Malaysia. Please pay attention. The live broadcast will begin shortly. The link to the certificate of attendance will be provided at the end of the session. Please make sure it is filled within the stipulated time. Thank you.
Bismillahirrahmanirrahim. Assalamualaikum, good evening and hi to all teachers, parents and the wonderful students. Welcome to Pusat Tuisyen Academy YouTuber, a joint venture with Didik and Kelab Guru Malaysia with the hashtag bermula percuma, selamanya percuma. So before we proceed, let's begin our session with the recitation of Umul Kitab Al-Fatihah, and for the non-Muslim, please take a moment of silence. Okay, so how is everyone doing today? So my prayer is that everyone is in the best of health and ready to proceed with today's class. Let me introduce myself first. I am Madam Rosmaya as your moderator and also a control host for today. I am a Form 6 Physics teacher at SMJKU Hua Kajang. And the most important person today is our presenter, Teacher Nun. Okay, Cikgu Nun, she is from College Matrikulasi Negeri Sembilan. So let us give a warm welcome to our presenter. Okay, so for the record, we are now live on Teacher Nun's channel. So as a sign of support to Teacher Nun for the hard work in preparing today's lesson, so please subscribe her channel and not forgetting to subscribe my channel too. So as usual, the lesson will last approximately 1 hour. So the certificate link and the credit claim link will be given at the end of this session. Remember that you can only use Didik email and more email to claim the certificate for credit claim. So you need to collect 1 letter and 5-digit codes. I repeat, 1 letter and 5-digit codes, which will be announced separately 3 times during our class today. So be sure to follow the class up until the end to get the complete code for the credit claim. So I would also like to remind students to use appropriate language and also use appropriate profile picture if you wish to post comments in the chat box. I'm pretty sure all of the students here are excellent students who will uphold a positive classroom environment. So please give your full cooperation in making this class a lively one. So stay focused, and if you have any questions, so please write on the chat box and Teacher Nun will try to provide you with the answers. So before I pass this session to Teacher Nun, okay, I will announce the letter and the first 2 digits code for credit claim. So the codes are A, letter A, and number 30. Okay, 30. Okay, so without further ado, please welcome Teacher Nun to start her presentation.
Okay, Assalamualaikum warahmatullahi ta'ala wabarakatuh. And hi everyone, how are you? Okay, thank you so much, Madam Rosmaya. My name is Madam Nun. So for today's class, as usual, we'll continue to do the revision for the matriculation and STPM topic. Before we start, I just want to introduce you in our academy YouTuber. We have a lot of subject. Okay, this is the physics prayu lead by Madam Rosmaya. Okay, and then we have mathematics prayu. Okay, lead by Teacher Im. And we also have the biologist prayu lead by Cikgu Faiza. And for the chemistry lead by Cikgu Shahnun. For the perakaunan and ekonomi prayu team lead by Madam Fizi. Okay, so you can get a lot of video, you can learn a lot during our tuition. Our academy YouTuber also have apps. Okay, you can download from the Google Play. You can get a lot of video, include the physics video for you to refer. Okay, so now we go to our objective today, which is we want to do the revision and exercise for the, if I'm not mistaken, this is the last topic for the matriculation and semester 3 for the STPM, which is nuclear physics and radioactivity. Okay. So for this topic, nuclear physics and radioactivity, actually I will discuss the past year's question for the matriculation. Okay. So nuclear physics and radioactivity, this topic are divided into two parts. So I will discuss two in the two part lah. Okay. So the first part is about the nuclear physics. So in nuclear physics, you will learn about the mass defect, okay, binding energy per nucleon, and also a graph of binding energy per nucleon versus mass number or nucleon number. So this is the four important things, very important for the nuclear physics subtopic. Okay. Because of that, let's go to the first question. Okay, before that, I will discuss overall uh, what is the each part just now. Okay, the first thing is mass defect, right? So mass defect is represented by the symbol of delta M. It is defined as the mass difference between the total mass of the constituent nucleon and the mass of the nucleus. So in terms of equation, we can write down that the mass defect delta M is equal to Z MP plus N Mn minus with the mass of nucleus. Okay, where the Z is the number of proton or electron or atomic number, N is the neutron number, MP is mass of the proton, and Mn is mass of the neutron. M nucleus is represent the mass of the nucleus. Sometimes the question in the question they give the atomic mass, not the mass of the nucleus. So what you need to do, you need to calculate the mass of the nucleus. Okay, referring to the atomic mass given, you minus with the number, the Z, number of electron, times with the mass of electron. Because of nucleus is only consists of proton and neutron. Okay, so you need to read the question carefully and identify the information given correctly. Okay, so the next one is the binding energy. The second thing is binding energy. The symbol is EB. So for the binding energy of a nucleus, it is defined as the energy required to separate completely all the nucleon in the nucleus. Okay, given by the equation of EB, which is equal to delta M, which is mass defect just now, times with the C square. Okay, so binding energy can be in the joule or mega electron volt unit. Mass defect can be in the kilogram or in the atomic mass unit U, and C for the speed of light is in the meter per second as usual. Okay, so this is the unit that relate when we want to do the calculation for the binding energy, which is we have the atomic mass unit. To relate the atomic mass unit U with the kilogram, it is equal to 1U equal to 1.66 times 10 power of negative 27 kilogram. Actually, it is depends on the question. Sometimes the question state the unit that, the final unit that they want. And also in terms of mega electron volt unit, so 1U is equal to 931.5 mega electron volt per C square. I will show you when and how we use this relationship. And for the energy instead of in the joule, okay, as a unit, so we also can give in the electron volt unit, where the relationship is 1 EV is equal to 1.6 times 10 power of negative 19 joule. Okay. So the next one is the binding energy per nucleon, okay, which is it is defined as the energy per nucleon required to completely separate the nucleons, okay, in the nucleus. It is given by binding energy divided by the nucleon number A or mass number, okay, and relate to the binding energy per nucleon, we have a graph of binding energy per nucleon against nucleon number or the mass number. So from this graph, what you can explain or what can you get? What information that you can get from this graph? So we refer when you want to explain, you can refer to the mass number, okay, or number of nucleon, where for the nucleus with the mass number between 0 to 20, we said it is a light nuclei. So for this light nuclei, the binding energy per nucleon is increased from 1 mega electron volt to 8 mega electron volt. Okay, increasing of the binding energy per nucleon for the light nuclei. And then for the nucleus with the mass number from 50 to 80, okay, this is the nuclei with the highest binding energy per nucleon. The range of the nuclei with the highest binding energy per nucleon, which is around 9 mega electron volt, and the most stable nuclei is ferrum 56 with the binding energy per nucleon 9 mega electron volt. Okay, so for the nuclei with the mass number above 80, okay, so the binding energy, if you look at the graph here, the binding energy per nucleon is decreasing. Okay, and for the range of mass number from 200 to 240, we consider it is a heavy nuclei. So heavy nuclei is a nuclei that which is not stable, unstable, and it is quite radioactive. Okay, so this is all the information that you can get from the graph of binding energy per nucleon against nucleon number. Sometimes so you need to sketch and you need to label the graph. So you just need to take note. There are few part, especially the mass number, the range of the mass number. Okay. So this is the overall about topic nuclear physics. Okay, now we go to the our exercise. So if you look at question number 1, uranium isotope, which is U238, has atomic mass of 238.0.05060783 U. So please be careful with the amount given. And do take note that it is a atomic mass. Okay, so what can you, when you read the question, what can you get from the question? Okay, take a look at the given information. So given the uranium 238, so referring to this isotope, so we can identify that the mass number or nuclear number is 238, and then the atomic number is 92. So the nucleon number is 238, mass number minus with atomic number or proton number or electron number, which is equal to 146. And I just identified here atomic mass is given as 238.05078 U in the atomic mass unit. So first we need to calculate the mass defect in atomic mass unit. So this question is quite special because of they guide you what you supposed to find out one by one. Okay, for example, first we need to calculate the mass defect and stated in the U unit. So to calculate the mass defect, make sure that as I said in my explanation just now, you need to identify the given info. If the question gives you atomic mass, meaning that you need to calculate the mass of nucleus first. So for the mass of nucleus, it is equal to mass of atom minus with Z times with the mass of electron. And all this information is given to you in the question during the final exam. So for example, mass of electron, mass of neutron, mass of proton is given to you. You just need to refer to the given information. Please refer to the given information, the value. So in this case, we substitute the mass of atom, and then Z here is 92, and mass of electron 5.49 times 10.94 U. And then you will get the mass of nucleus is 238.00025 U. This is mass of nucleus. We want to calculate the mass defect. So the second step, then you can calculate the mass defect using this relationship. Now we have the mass of the nucleus. We just need to substitute following the equation. Substitute the Z, mass of proton, which is 1.007277 U, N, number of neutron 146, and the mass of neutron 1.008665 U. And mass of nucleus you have calculate here, just substitute, and then make sure that you press your calculator carefully. Okay, because of this is a lot of decimal places here. So you will get that the mass defect is equal to 1.934299 U. In this case, because of the question want you to give in the atomic mass unit. Okay, so this is the answer for the mass defect. Now we want to calculate the binding energy in the mega electron volt. Okay, so just now we have calculated the mass defect. So to calculate the binding energy, we will use the mass defect that we have calculated in A. So here is mass defect 1.934299 U. Okay, remember in the atomic mass unit U, but the relationship U, actually tadi just now I show you the relationship U with the mega electron volt unit. So we just replace U with the 931.5 mega electron volt per C square. That's the relationship actually given to you in the final exam. So no need for you to remember, but make sure that you substitute correctly. And don't forget, if you refer to the binding energy equation, delta M times with C square. So in this case, no need to substitute the value for C because of we want the binding energy in mega electron volt unit. Okay, we want the energy in the mega electron volt unit. So this is the U we have replaced with this value, and then C here can be cancelled with this C square. Okay, C square can be cancelled. So the binding energy in the mega electron volt unit given by 1802. If you calculate, you will get 1802 mega electron volt. Okay. All right. So please take note how you substitute. Because of substitutions, there is a marks for the substitution. Okay, for question number C, we want to calculate the binding energy per nucleon. Okay, so for the binding energy per nucleon, we know that the relationship is EB over A. Our nucleon number or mass number just now is 238. So we just divide the binding energy in the mega electron volt unit, divide by 238. So you will get the binding energy per nucleon, which is equal to 7.57 mega electron volt per nucleon, because we have divided with the number of nucleon. Okay, or mass number. So this is the answer for question number C. And for question number 1, this is step by step how to get normally the final calculation about the binding energy per nucleon. Okay, and this question is quite good because of they guide you one by one. First, calculate the mass defect. Second, binding energy, and then calculate the binding energy per nucleon. So you can save a lot of marks. Okay, if you correct in part A, part B. Okay, part B and section C. Okay, take a look at question number 2. Have you tried? So I'm sure that if you try to answer question number 1, you also can answer question number 2. But if you look at question number 2, for question number 2, you need to calculate the binding energy per nucleon of a sodium nucleus, okay, Na23 in mega electron volt per nucleon. Binding energy per nucleon, right? And given the atomic mass of sodium is 22.989769 U. Okay, if you look at this question, actually this question same with the previous question. It is only directly you need to calculate the binding energy per nucleon. There is no shortcut. You cannot get one equation and you use one equation and then you can get the answer. In this case, you still need to follow. That's why I just pick up this question. Okay, before we see the solution, as usual, referring to the nucleus given to you, we can identify the mass number, which is 23. The atomic number is 11. And for the nuclear number, 23 minus 11, we get 12. Okay, and I also highlight here, given the atomic mass, same with the question number 1. So what you need to do first step before you calculate the binding energy per nucleon, of course you need to calculate the mass of the nucleus first. Okay, so we just follow the same step, meaning that even this question is quite short, only 2 lines compared to the previous question, but the step is still same because you want to calculate the same thing by the energy per nucleon finally. Okay, so here I just show you to calculate the mass of the nucleus for this sodium nucleus. Okay, Z is 11. Okay, I substitute 11 and this is the mass of the atomic mass unit for the electron. You get the mass of nucleus 22.98373 U. Just follow your calculator in this case. Yeah? Normally up to six decimal places. And then to after you get the mass of the nucleus, okay, you can calculate the mass defect. Okay, for the mass defect, ZMP plus NMN minus M nucleus. Okay, mass of the nucleus we have calculated earlier here. So we substitute the value, and do take note, don't confuse. That's why I state clearly at this side at the given information, because of when you want to substitute the z, the n, make sure that you pick up the correct value. Do not only what we say congak-congak. So make sure that you calculate exactly. Okay, and then substitute the mass of the proton, mass of the neutron, and also the mass of nucleus that have calculated. You will get the mass defect. Okay, after the mass defect, before you find the binding energy per nucleon, I suggest you to calculate the binding energy first. So for the binding energy, as usual, because of mass defect is in the atomic mass unit, so the U here we replace with 931.5 mega electron volt per C square. Okay, and then C square is here, we just bring forward, and then no need to substitute, but because of we can cancel both C square, so you will get the binding energy in the mega electron volt unit, which is equal to 186.6 mega electron volt. Okay, 186.6 mega electron volt. Okay. Please remember, this is the step by step I show you. So to calculate the binding energy per nucleon, okay, divide the binding energy with the mass number or nucleon number, which is 23. You will get that the binding energy per nucleon 8.11 mega electron volt per nucleon. Can you see that even the because of the question is direct, meaning that you need to calculate the binding energy per nucleon. Please remember the step and please alert with the information given. So let's say if the question give you the mass of nucleus, not the atomic mass, yeah. Let's say the question give you the mass of nucleus. So how you want to solve? Okay, take a look at the question number 3. All right. So question number 3 stated that given the mass of the nucleus boron is 11, boron B11, B11 is 11.008757 U. You need to calculate the binding energy per nucleon. Okay, directly you need to calculate the binding energy per nucleon. But what is the step? Okay, how's the step? We do the same thing. First, from the given, what you can get from the information given, from the nucleus given, so you can identify the mass number 11, and then the atomic number 5, the nuclear number is 6, and okay, in this case, if you look at here, the mass of a B nucleus, meaning that the value here, it's not, it's look like that, not many different. We don't know the different actually. So this is the mass of nucleus. The different is here in the previous question, question number 1 and question number 2, given the mass of atomic mass. Okay, so in this case, the question give you the mass of the nucleus. So from the mass of the nucleus, we can calculate directly the mass defect. Okay, no need for you to calculate the mass of nucleus because of the mass of nucleus is given. Shorten one step compared to the question number 1 and 2, right? So you can calculate the mass defect, which is equal to when you substitute. And as I said, make sure that take note for the number of proton or the atomic number and mass number when you substitute. Sorry, nuclear number 6. Yeah, when you substitute, and mass of the nucleus as given. So you will get the mass defect. The next step after the mass defect is the binding energy. Okay, you calculate the binding energy. Choose the shortest way lah. In this case, because of the mass defect is in the U unit, so U will be replaced with 91.5 mega electron volt per C square. Okay, and then the C square here we can cancel. So you get the binding energy, which is 74.16 mega electron volt. And to calculate the binding energy per nucleon, okay, binding energy per nucleon, we divide by the mass number, A, or nuclear number. So you get the binding energy per nucleon, which is 6.74 mega electron volt per nucleon. Okay, so you have answered the question because of the question not state in what unit. So I just give you if the question want you to calculate the binding energy per nucleon in the joule per nucleon, let's say in the joule per nucleon. So what you need to do, so referring to the mass defect you have calculated earlier, we have the relationship of atomic mass unit, right? 1U is equal to 1.66 times 10 power negative 27. We want to change to the kilogram unit. Mass defect can be in the kilogram unit. So we change mass defect from atomic mass unit to the kilogram. And then, okay, this part that I want to highlight. When you have the mass defect in the kilogram, when you want to calculate the binding energy, you substitute the mass defect in kilogram. And for the C, you need to substitute C in the SI unit. 3 times 10 power of 8 square. Okay, because of the mass defect is in the SI unit. When you calculate, you will get that the binding energy, which is equal to 1.188 times 10 power negative 11 joule. So for the binding energy per nucleon, you divide by the by the mass number 11. You will get the answer for the binding energy per nucleon in the joule per nucleon unit. Also can. It is depends on the question. What the question want. You need to refer to the question. Okay, but the way is like that. You need to familiar to use the unit conversion. Okay, unit conversion between the atomic mass unit and the SI unit. Okay, so maybe this is enough for the nuclear physics. Now we will continue with the radioactivity. And for the radioactivity, we will discuss about the decay process, decay law or decay activity, decay constant, and half-life. This is the important terms. So I just highlight the first. For example, what is radioactive decay? It is defined as the phenomenon in which an unstable nucleus disintegrates to acquire a more stable nucleus without absorbing an external energy. So the radioactive decay is a spontaneous reaction and unplanned, cannot be predicted, independent physical conditions such as pressure and temperature, and also there is a chemical change. So this is the particle, for example, alpha particle, beta particle will be emitted or gamma ray will be emitted during the decay process. Okay, so what is the decay law? So decay law state that the decay rate, which is dN per dt, is directly proportional to the number of radioactive nuclei present in the source, N. Okay, N is the number of radioactive nuclei. So it is represented by dN per dt equal to negative lambda N. This is the relationship between the decay rate and also the number of radioactive nuclei remain. Okay, remain or initial. So this is all the sign, the meaning of each sign. We have the lambda here. In this case, lambda is the decay constant. Okay, n is the number of nuclei present at a time, and the negative sign indicate that the number of nuclei present decrease with time. Okay, so now we go to the activity. Okay, what is activity for the radioactive decay? So activity is also actually equal to the rate, the decay rate. dN per dt is decay rate, or we can write down as lambda n. A is also equal to lambda n. This is can relate the activity with the number of nuclei, number of radioactive nuclei. Or in terms of equation, if you want to calculate the final activity, so the equation is A is equal to A naught exponent negative lambda t. Okay, A is activity at the present, A naught is initial activity. Okay, and the unit for the activity, do take note, this is sometimes we confuse because it's for the activity we have 3 units. We can give in the decay per second, or Curie, okay, CI, or becquerel, BQ. And the relationship between the unit is 1 becquerel is equal to 1 decay per second, and 1 Curie is equal to 3.7 times 10 power of 10 decay per second. So this is very important relationship. Okay, the same thing with the previous subtopic. You need to consider what the question give you, what the information given. Okay, and then we also have one another terms which is we call it this decay constant just now, which is lambda. So it is defined as the probability that a radioactive nucleus will decay in 1 second with the unit of per second. Okay, and referring to the decay constant, we have the relationship, okay, with the activity and also for the number of nuclei, remaining nuclei. Okay, remaining number of nuclei, and n naught is the initial number of nuclei. Okay, and from the decay constant we have the another terms which is we call it half life. half-life for the radioactive. Because of radioactive, it is the process will not end, so it is very difficult for us to calculate the end-ish of the radioactive. Because of that, scientists introduced the half-life. We can calculate the half-life of each radioactive. Because of radioactive, so far we can the process is not end. Okay, so half-life represent by T half, which is defined as a time take as time takes for for half of a given number of radioactive nuclei to decay. That's we call it half life. And the relationship is half life, the half is equal to ln 2 divided by the decay constant. So that's the relationship. And for this all equation and also the relationship, it is a lot function. When we answering the radioactivity, the question that relate to the radioactivity. Okay, so Madam Rusmaya, maybe we want to break before I continue. Your microphone.
Sorry, yeah. Okay, so we have already go live for 30 minutes. Okay, so we will take a break. So before we take a break, okay, I will announce the third digit code for credit claim. So listen carefully, everyone. Okay, the digit is number 5. Okay, the digit, I repeat again, the digit is number 5. Okay, stay tuned, everyone.
Berita baik untuk semua. Kini, Akademi YouTuber memperkenalkan sistem mata gancaran kredit AYU untuk dikumpul. Jom ikuti kelas tuition live AYU untuk mengumpul kredit AYU dan berpeluang menebus hadiah-hadiah yang menarik. Hadiah bernilai lebih RM10,000 disediakan secara percuma untuk pelajar seluruh Malaysia. Apa tunggu lagi? Tebus ganjaran hebat ini sekarang. Layari www.academyyoutuber.com untuk maklumat lanjut.
Okay, welcome back, students. Madam Nun, you may proceed with your presentation.
Okay, thank you, Madam Rosmaya. So now we have discussed the second subtopic, which is about the radioactivity. Now take a look at the exercise of the question. For the question number 4, a prepared sample of radioactive isotope has an activity of 10 millicurie. After 4 hours, the activity is 8 millicurie. So, referring to the question, this is the given information, and please do take note given to you. Understand carefully. For example, after initial activity of the radioisotope is 10 millicurie. After 4 hours, it decrease to 8 millicurie, and given the relationship here. Okay, so first we need to calculate the half-life of the isotope. Okay, so for the half-life of the isotope, what we need to do, remember the equation for the half-life, which is ln 2 divided by decay constant. So to calculate the half-life, okay, you need to know the decay constant first. So to calculate the decay constant, referring to the activity equation, okay, please substitute correctly. In this case, I not change to the M is milli, milli, so I just substitute 8 milli, and a note initial activity is 10 milli because of we can cancel this milli. Okay, so this is the step by step of solving. To first we want to calculate the decay constant. We use this equation because we have the T after 4 hours. Okay, so do take note our unit here. I substitute 4, meaning that the unit for the decay constant when you calculate, you will get that in 0.0558 per hour. Okay, so if you want to, sometimes even if not stated what unit you need to state, I just show you. Just if you want to change to the SI unit, you can change to the per second. Okay, for the decay constant, and then you can calculate the half life. Okay, referring to what question 1, half life is equal to ln 2 divided by lambda. Okay, so lambda is here. Okay, in this case I use per hour, so you will get the half-life in the hour unit is 12.42, and if you replace or if you substitute with per second unit, so you will get 4.47 times 10 power of 4 second. I hope that you can try one of it. Okay, either one, it is okay because of the question not state in what unit you're supposed to give your answer. Okay, so this is A. You calculate the half-life, okay. And now we want to calculate the number of the isotope in the prepared sample. Number of the isotope in the prepared sample. Prepared sample to meaning that in the initial sample. So in this case, I change to the decay per second unit. So if for the 10 millicurie, it is equal to 3.7 times the power of 8 decay per second, meaning that I just times with 3.7 times 10 power of 10, I get the initial activity, which is 3.7 times 10 power of 8 decay per second. Okay, so to calculate the number of the isotope in the prepared sample, we can use this relationship, which is because of we want to calculate the anode. Okay, so we have the anode here, initial activity. So we want to calculate the number of isotope in the prepared sample. We have the decay constant we have calculated earlier in the first part. So we just substitute, you will get that the anode, the number of isotope in the prepared sample or initial number of isotope is 2.39 times 10 power of negative 13 isotope. Okay, because of the question said number of the isotope, you can state the unit as isotope. Okay, uh, and for question number C, we want to calculate the activity 30 hours after it is prepared. Okay, 30 hours. So our T now is 30 hours. Okay, which is we change to the SI unit as because of our A note just now in the per second in the SI unit. So when you change to the second, and then you can substitute in the activity equation where our A note is 3.7 times the power of 8 E negative 1.55 times the power of negative 5 is the decay constant. 1.08 times 10 power of 5 is the T for the 30 hours. 30 hours in the second unit. Okay, and then when you calculate, okay, use your calculator, you will get that the activity of the sample after 30 hours, it is prepared is 6.94 times 10 power of 7 decay per second. Okay, so it is quite easy, right? Step by step, we just apply the equation. But the most important is you substitute correctly and you press your calculator correctly. Okay. Now we go to the question number 5. So referring to the information given or referring to the question, a sample of Bi211 contain 2 times 10 power of 9 nuclei. So this is referred to the initial nuclei, initial number of nuclei. Okay, given the half-life of Bi211 is 2.14 minute. Okay, the half-life, the half is 2.14 minute. Change to the SI unit, calculate in the second. Okay, which one easy for you? So we want to calculate the initial activity in the decay per second. So if you refer initial activity is A naught. A naught. Okay. Take note. We want to calculate the A naught. We have the N naught and also the half-life. So we know the relationship for the A naught is lambda N naught. Am I right? So first we need to find the lambda or the decay constant from the half-life. This is actually considered as our hidden information. Okay, can consider as our hidden information. For the decay constant, you can calculate by substituting the half-life in the second. So you get the decay constant in per second. And then to calculate the initial activity, you see we can use this relationship because of N naught is given. Decay constant we have calculate. You just need to substitute correctly in the equation and you will get that the initial activity in the decay per second, okay, in this unit is 1.08 times 10 power of 7. Okay. So this is the answer for the initial activity of this sample. Now we want to calculate the number of the nuclei remain after 42.8 seconds. Number of nuclei remain meaning that we want to calculate the n. Okay. So how we can use the relationship for the number of remaining nuclei, and then referring to this relationship, we substitute a node, which is 2 times 10 power of 9. And then the decay constant is 5.4 times 10 power of negative 3. That's why it is very important. Even the question not ask us to calculate the decay constant, you need to show the calculation for the decay constant. Actually, there's no marks for the calculation for the decay constant. But if you show the calculation, and see in the part B, we still need to use this value. So it will help you to reduce your time lah to calculate many times. Actually, you can calculate in the calculator, but better you write down in your solution so that for the next question you can refer again. Okay, so you can substitute the value for the decay constant and also the time, because we want to calculate the number of nuclei remaining after 42.8 seconds. We just substitute because of our decay constant is also in the per second unit. Okay, when you calculate, you will get that the remaining nuclei is 1.59 times 10 power of 9 nuclei. Okay, so if you look at very familiar the equation that relate to actually this topic, kindly speaking, it is quite easy to score, but you need to read the question carefully and be careful with all the information, the unit for the information and the unit given. Okay, make sure that you need to particular, don't mix the unit. Do if you use the SI unit, change all to the SI unit. Okay. All right, this is question number 5. For question number 6, okay, take a look at question number 6. I hope that you have tried to answer the question, and then please compare your solution with my solution. Okay, for question number 6, the activity of a sample of radon 222 is 200 becquerel. Okay, now they use the activity unit as becquerel. Just now we know the activity, there are 3 unit, decay per second, becquerel and curie. Okay, so the half-life of radon is 3.8 days. Okay, referring to the question. A node is represent 200 becquerel, and the half is changed to the SI unit, 3.28 times 10 power of 5 second. Alright. First, we want to calculate the decay constant for this radon 222. Okay, to calculate the decay constant, because of the half-life is given to us, it is quite easy, right? So we just refer to the equation for the half-life and then substitute the half-life given. Then you will get the decay constant, which is equal to 2.11 times 10 power of negative 6 per second. This is also very important for you because of 3.28 times 10 power of 5 is in the second unit. So for the decay constant, it is per second. Alright, for question B, calculate the number of radon atoms in the sample. Okay, the number of radon 222 atoms in the sample. So we want to calculate the n, okay, initial number of the sample. So we refer to this relationship. Actually generally A is equal to lambda n. So when we want to calculate the initial value, so the activity is supposed to be the initial activity. So A naught is equal to lambda n naught, and in our n naught is it is okay to use becquerel in this because a becquerel is also equal to 1 becquerel is equal to 1 decay per second. So if 200 becquerel, if you want to change to the SI unit, it is equal to 200 decay per second. Okay, same. So no worries, we can use directly. And then for the decay constant, we use the value that you have calculated in A, substitute in the question. You can calculate the number of radon sample. Initial is 9.48 times 10 power of 7 atoms. Okay, because we want to calculate the radon atoms. And if you look at question number C, how long? So how long does it take for the activity to decrease to 60 becquerel? Meaning that the decay process decreasing the activity to 60 becquerel. We want how long? Meaning that we want to calculate the T. Because of that, what equation that we can choose? Because if you refer to the information, we have the initial activity, we have the final activity, and also we have the decay constant. So we can use the activity equation to calculate the T. Okay, substitute A, which is 60, the final activity, 60 becquerel, A naught is 200 becquerel, the decay constant is 2.11 times 10 power of negative 6. So you will get the T, which is equal to, uh, okay, this is the way, we take the ln, 60 divided by 200, and then you will get the T. Okay, I just give here because of our decay constant is in per second, so the unit in second is 5.71 times 10 power of 5 second. And if the question want you to calculate in days, for example, because of initially the half life is in days, so it is equal to 6.6 days. Either one. It is, as I said, it is refer to the question. What the question want? Please refer. Okay. If the question asks you to give not mentioned in any unit, you can give in any unit that you comfortable. Okay. But I prefer SI unit. Okay. So now we go to the question number 7. For question number 7, the activity of a radioactive source decreases by 5% in 28 hours. Calculate the half-life of the source. See, the question still, it is around the half-life, decay constant, activity, initial activity, remaining nuclei. We just need to calculate the terms, all these terms. But if you look at the question, take a look at the information given. It not mention anything. It just state that the activity of the radioactive source decreased by 5%, meaning that we can assume, okay, because of they give in the percentage, so we can assume that the initial activity is 100%. And then in 28 hours, it decreased to 5%, meaning that the final activity is 95%. You understand, right? All of you. So I hope that you understand. Read the question carefully. The activity of the radioactive source decreased by 5%. It is decreased 5% in 28 hours, meaning that final activity is 95% left. Okay. So how to calculate the half-life? Given the T, because of this decreasing of the activity of the radioactive source is 28 hours. So we have the A node, we have A and also T. We can use the activity equation. But before we use the activity equation, we need to calculate the decay constant. If you look at here, there is no decay constant, right? So referring to the information, calculate the decay constant first, referring to the activity equation. So you can substitute because of percentage, we can cancel at both sides. So you can use this value, even it is not in the becquerel, it is not in the Curie unit, decay per second, it's not in that unit, but we can use this way because it will give the same value. So when you substitute, and do take note that we just substitute 28 hours, okay? Because of that, when you calculate, you will get that the decay constant is in the hours per hours unit, 1.83 times 10 power negative 3 per hours. Okay. But take a look. Don't careless. The question want you us to calculate the half life. Okay. So to calculate the half life, as usual, the equation for half life is ln 2 divided by lambda. Okay, lambda is the decay constant that we have calculated here. We just substitute, and then you will get the answer for the half-life is 3.78, 3.79 hours. So in this case, it's not stated what you need that you're supposed to give your answer. So you just can follow the question unit. Okay, the question, the unit in the question. So our answer for the half-life is in the hours unit. Okay. I hope that everybody on track with me. Now we go to the question number 8. For question number 8, 8 days after its preparation. Okay, please read the question carefully. The activity of the sample of radioisotope was 540 decay per second. So take a look here, the list of information that I write down. T is equal to 8 days. So A activity after 8 days after the preparation is 540. And then the activity further reduced to 200 decay per second. Okay. After 14 days, meaning that A14 activity after 14 days from the date of preparation is 200 decay per second. And T is equal to 14 days lah for this A14. Okay, but okay, take a look here. Actually, for the sample, to for the activity of of that sample to reduce from 540 to 200 decay per second, it takes how many days? That's the hidden information that you need to identify. How many days? So if you look at 450 is after 8 days of preparation, and 200 decay per second is after 14 days, meaning that it takes for that sample to decay from 540 to 200 is 6 days. So it is very, very important. When you do the calculation, for example, when you calculate the decay constant, we use the activity equation. So in this case, I just rewrite the equation following the information. For example, we have the info of activity after 14 days preparation, activity after 8 days preparation. Okay, I just write down there. But what is the difference? When I write down like this, we will remember to substitute the T. T is not 14 or 8. T is equal to 6. Okay, that's actually the hidden info, which is very, very important. Normally, students do a mistake in this part. They will substitute the T with 14. No, it is actually the sample reduce the sample decay is only in 6 days. Please take note about that. Even the equation said that initial activity and A naught is initial activity, A is final activity. You still need to consider the range, how long the activity decay. Okay, so T is very important here. And when you substitute, you try to solve the question, you will get that the decay constant is equal to 0.166 per day. Because I not change the unit just now. So the unit is per day. Okay. And then for the half-life, so it is very easy. We use the equation for the half-life. We substitute the decay constant. So you will get the half-life of this sample is 4.18 days. Okay. And just to remind again, because there are part A and also part B. So make sure that you need to calculate carefully part A, because of if you wrong in part A, can you see what happened to part B? Okay, do take note about that. Now we go to the question number 9. So for question number 9, a sample of radioactive nuclei, which is PT199, has an initial activity of 7.56 times 10 power of 11 becquerel. Okay. So after 92.4 minutes, the activity has decreased to 9.45 times 10 power of 10 becquerel. So if you refer to the information given, so A naught is equal to 756 times 10 power of 11 becquerel. Okay, initial activity. Okay. And then for the A, take a look, T is equal to 92.4 minutes. So I change to the SI unit, which is 5544 second. All right, and the activity at this time is 9.45 times 10 power of 10 becquerel. So we want to calculate the half-life of the nuclide. What is important for the half-life? It is a decay constant, right? So for the decay constant, of course, referring to the information given, you need to calculate the decay constant first. Remember the unit, the equation for the decay constant, we refer to the activity equation. So referring to the activity equation, okay, substitute the uh, activity after 92.4 minutes, okay, and then initial activity is 7.56, okay, times 10 power of 11. And the T, we have changed to the SI unit. Okay, as I said, becquerel, don't worry with the becquerel, because our becquerel is also equal to decay per second. The unit is SI unit. Okay, name only. Okay, so we can substitute 5544. And then when you calculate, you will get the decay constant, which is equal to 3.75 times 10 power 94 per second. We want to calculate the half-life. So for the half-life, just use the equation for the half-life, substitute the decay constant, and you will get the answer in second. You can see we just every time you want to calculate the half-life, you need to calculate the decay constant. Okay, but the difference is only the way the question, the information given in the question. So it is your part actually. You know the solution, but you need to read the question carefully to identify the information given, especially the unit. Actually, it is a very easy mistake. You all students do normally because of they not particular with the unit. Either you use as a unit or you not change the unit. Whatever it is, make sure that you do a lot of exercise will help you to reduce your mistake actually. Okay. And that's why if you look at to our discussion, I repeating calculating the same thing, but the question is in the different way. Okay, the information given in the different way. Okay, now take a look at the B, question number 9B. How many radioactive nuclei were initially present in the sample? So meaning that we want to calculate the N note, initial. Okay, so how we have the relationship between the A note and the N note. Why? Because of initial activity is given to us. Am I right? And then we have calculated the decay constant. We just need to substitute in the equation. So you can calculate the N note. Okay, because of that, for the remaining nuclei is equal to 2.016 times 10 power of 15 nuclei. Okay. It is. I'm sure that if you can identify the correct information, this part is very important, and then the rest will be correct. Even you know all the equation, but if you cannot identify correctly the information given, it is. I will not sure that you can get full marks. Okay. Now we go to the last question for today's discussion. So, last question is calculate the activity of a 5 microgram natrium 24, which has a half life of 14.9 hours. You want to calculate the activity. The only given is the mass of the sample, okay, and then the sample itself, also the half life. So, if you refer to the given information, the hidden info that we have is no hidden info. The mass is given 5 microgram. MR is molar mass is 24 gram. Okay, and then the half life. So for the half life, I change to the SI unit, which is in second. So first we can to calculate the activity because of like this. Remember when you to calculate the activity, and if you refer, you have the half life, meaning that you can calculate the decay constant. So the activity can be calculated using the equation of A is equal to lambda n. Am I right? So now we want to calculate the number of nuclei. Number of nuclei. So, referring to this equation, to get the A, you need to know the decay constant and also the N. So now we want to calculate the N. So how to calculate the N? Referring to the given information, if you look at here, okay, N that we want to calculate, we use this relationship, this equation. N, number of nuclei, divided by the Avogadro number is equal to the mass of the nuclei divided by the molar mass of that nuclei. So we just substitute the Avogadro number, which is given to you, of course, in your final exam. And then the mass of the nuclei is 5 micro times 10 to the power negative 6, of course. And then the molar mass is 24. Okay, because of gram can cancel, so no need to change to the kilogram. And if you calculate, you will get that the N, the number of nuclei, is 1.254 times 10 power of 17 nuclei. And then for the half-life, because of from the half-life equation, because we have the half-life info, you can calculate the decay constant. So substitute the value, you will get the decay constant is equal to 1.229 times 10 power negative 5 per second. And from these two information, information that you have calculated, you just need to substitute correctly in the equation. Okay, and then you will get the activity, which is equal to 1.62 times 10 power of 12 decay per second. Okay, so I hope that I choose different types of question, but the solution is the same. Actually, that's only the equation that involved. You just need to know which equation that you want to use, what you want to calculate, to shorten your time answering the question. Don't take too long. If you know which equation, go direct and find what you're supposed to find out before for you to substitute in the final equation. Okay, so I think that's it for our discussion today. Thank you so much, everyone. Do take care of yourself, and I wish you all the best in your final exam, any exam that you will take. And please, if you have any comment, please comment my presentation so that I can improve my next presentation. And please like and share if you think it is a benefit. Please share with your friends, and don't forget to subscribe our channel. Okay, so I give back to Madam Rusmaya. Thank you so much, everyone. Okay, Madam Rusmaya.
Okay, with the end of today's session. So congratulations to those who are able to follow our session from the beginning till the end. Okay, before we end our session for today, I will announce the fourth and the fifth last 2 digits code for credit claim. So the digits are 4. Okay, double 4. Okay, 4 and then another 4. Okay, that's the last 2 digits code for credit claim. Okay, so all of you, please stop posting your comments for a while. And if you haven't clicked the subscribe button, so please do so. Make sure it turns to grey color, not red color. And activate the icon bell so that you will not miss the next class session. Okay, then if you find the lesson was beneficial, click like, the like button, and share to your friends on your social media. So spread and share the goodness. So once completed, type done on the chat box before the certificate link and credit clip link is given as a token of thank you for your dedication in joining the free class, online class today. So I will paste the link in the chat box. Okay. Okay, done. Okay, the certificate link and credit claim are already given in the chat box. So please take note, the link will end half an hour after this live. So make sure to use the EDD email or MOE email only to log in. So incorrect email used will not be entertained. So if you haven't got one, please apply. So the link to apply the EDD email is also already given in the chat box. If you wish to get more information on the online classes, so go to www.academyyoutuber.com. And to those who haven't joined EDD Junior Telegram, please do so. So once again, I would like to thank all of the students for joining today. And remember that the more classes you join, the more credit you can claim. And feel free to share this free tuition class to your friends and teachers all over Malaysia. So this is a collective effort from all the teachers throughout Malaysia for all the students throughout the country. So thank you too for being a YouTuber Academy supporter too. So I think that's all for now. So see you in another session. Ingat hashtag bermula percuma and selamanya percuma. Assalamualaikum. Stay safe. Same time. Okay, we meet again next week on Sunday at 5 p.m. Okay, bye-bye.
Wow, banyaknya hadiah menarik menanti anda. Wah, kini Akademi YouTuber mengambil inisiatif baru di mana memberikan hadiah-hadiah ini secara percuma. Ya, percuma kepada anda semua. Bagaimana caranya? Dengan mengikuti kelas tuition online percuma Akademi YouTuber sambil mengutip mata kredit, anda dapat menukarkannya dengan hadiah-hadiah yang menarik ini. Tunggu apa lagi? Segalanya percuma. Jangan lepaskan peluang tau. Dah dapat banyak hadiah menarik, takkan nak lepaskan peluang. Layari www.academyyoutuber.com sekarang untuk maklumat lanjut.
Dibawakan kepada anda oleh Akademi YouTuber.